Okay, today we are going to take a look at the second series topic, which is 9b, Taylor series. Taylor series, Maclaurin series. Let's take a look at these. Always FRQ number 6. It's always the series question. All right. First of all, we have to know, we must know the Taylor series for F about x is equal to c, where it's centered. Always has this pattern. Always. We have to know that pattern. Third derivative at c divided by 3 factorial times x minus c to the third power. The power always matches the derivative, which always matches the factorial. So everything is in that form. Everything. Every term is in that form. We begin with the no derivative term, which if we really wanted to, we could make that no derivative times x minus c to the 0 power divided by 0 factorial, because 0 factorial is 1. So if we really wanted to, we could even write this in that form. Okay? It is also important to know that the coefficient is whatever is in front of this thing. All right? These are the coefficients. The coefficient is not just the derivative. It is the derivative divided by the factorial. That's the coefficient. Okay? All right. Sine x is all the odds, alternating in sign, all the odds, odd powers, odd coefficient, odd powers, odd factorials. Cosine is all the evens, beginning at 1, which you can think of as x to the 0 over 0 factorial if you want to. So all the evens, e to the x, positives, and not just the evens, not just the odds, but all of them. Recognize functions in this form. For instance, f of x is 4x divided by 1 minus x cubed. It is in this form where a is 4x and r is x cubed. It's in that form. And if that's the case, the first term is 4x. That's your first term. To get to the next term, you multiply by x cubed. 4x times x cubed is 4x to the 4th. Multiply that by r, and that by r, and that by r, and keep on going. Okay, the radius of convergence, this converges when x cubed r, the absolute value of r, is less than 1, because this is geometric. I don't know why I didn't write that there. You guys add that. That is geometric. Okay, so this is the geometric series test there. All right, so like I said above, the coefficient of the 5th degree term is always the 5th derivative at c divided by 5 factorial, always. The coefficient of the 8th degree term is always the 8th derivative at c divided by 8 factorial. If you are asked to find the 6th derivative, if you're asked to find the 6th derivative of some power series, go find the term with x to the 6th in it and set its coefficient equal to the 6th derivative over 6 factorial. So the 6th derivative will always equal to 6 factorial times whatever your coefficient is in that power series. Okay? All right. You guys, what's the coefficient of this? Okay, the coefficient of that is not -1. It's not a 1 or a -1. It is -1 over the denominator. Okay? You can write this as -1 over 3 to the 4th times 4 factorial times x to the 6th. This is the coefficient. All right. The ratio test is used to determine the interval of convergence for any power series. Show all of your work at least 4 points, sometimes 5. Lagrange error bound works very similarly to how the alternating series error bound works. The only difference is that Lagrange is always in the form of a Taylor series term. Derivative x minus c to a power divided by a factorial. Okay? And there's one other difference. This is not just the derivative, it is the maximum derivative on an interval. The interval is always from your center, whatever your center value is, to your x in your approximation. Okay? So, on this interval, you want the maximum derivative. Sometimes that's just given to you. Oftentimes it's just given to you. This would be the maximum derivative. Okay? Other times you have to do a little work to get it. Leave it like that. Don't simplify it. Error is always positive, so ignore any negative in there. Always positive. Either ignore the negative or put absolute values around it, because in this case this would give you a negative number. It needs those absolute values. Alright, sometimes we take the derivative or integral of a series piece by piece, term by term, using the power rule. Okay? When writing a general term, check, put in an n value and see if you get one of your terms. And then, as always, don't be surprised if you're asked to do something different with a series. Okay? Alright, let's go do one. 7 minutes. Alrighty. Very good. We're going to start with number 1. It is extraordinarily easy to find these FRQs because on every exam it's always number 6. I don't have to write number 6 here because it's always a series. Okay? Number 6 is always a series. Alright. The Maclaurin series for ln of 1 plus x is given by this. Okay? There is the Maclaurin series they're telling us for ln of 1 plus x. On its interval of convergence, this series converges to ln of 1 plus x. Well, that's very true. That's true for every Maclaurin series, Taylor series. Let f be the function defined by this function. Write the first 4 non-zero terms and the general term of the Maclaurin series for f. Well, I notice the similarity between f and what was given to us. I have an additional x outside, which I might go ahead and write outside. Okay, there's that x. And then I have ln of 1 plus x over 3. This is the series for ln of 1 plus x. All I need to do is substitute in place of that x, x plus 3. In place of every x here, I'm going to put x, did I say x plus 3? X over 3. In place of every x, I'm going to put x over 3. So I'm going to replace that x with x over 3. I'm going to replace this x with x over 3. And when I do that, I'm going to have x squared over 3 squared. Please be kind to yourself and make it that way. Alright? And then I still have this 2 in the denominator, which I'm going to include in this other denominator. Plus, chances are we're going to have to use this. We're going to have to use our answer here. So you need to write it in a form where it's going to make it nice for you to use. So this will make it nice for us to use. Okay, I'm going to go to this, replace that x with x over 3. I'm going to have x cubed over 3 cubed. And then I have another 3 on the bottom right there. Minus, replace this x with x over 3, so I have x to the 4th over 3 to the 4th times 4. Hopefully you're seeing a pattern here on the bottom, right? Plus dot 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 plus negative 1 to the n plus 1. I'm replacing that x with x over 3. So I'll have x to the n over 3 to the n times n. Now, this is not a safe stop spot. It's not a safe stop spot because this, with this x out in front, it is not in the form of a Maclaurin series. If you're writing a Maclaurin series, it must be in the form of a Maclaurin series. So I'm going to go ahead and multiply through by the x. I'll have x squared over 3 minus x cubed over 3 squared times 2 plus x to the 4th over 3 cubed times 3 minus x to the 5th over 3 to the 4th times 4 plus dot 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 negative 1. All I'm doing is copying. Okay, x times x to the n is x to the n plus 1 over 3 to the n times n. First four non-zero terms and the general term of the Maclaurin series for f. Part B. Determine the interval of convergence for that series that we just wrote, the Maclaurin series for f. Interval of convergence for a Maclaurin series, ratio test. Unless our series is geometric, but this series is not geometric. Okay, so ratio test, limit, n goes to infinity, absolute value. I go to my general term. I ignore the negative 1 because of the absolute values. Ignore the negative 1, go only to this piece. Replace every n with n plus 1. X to the n plus 2 over 3 to the n plus 1 times n plus 1. Okay, and then we're dividing by the nth term. We're dividing by that as it is, which is the same as multiplying by its reciprocal. 3 to the n times n over x to the n plus 1. Okay, now we do the limit. Okay, the x's reduce, leaving a single x on top. I'm going to put that single x in my absolute values, a single x on top. The 3's reduce, leaving a single 3 on the bottom. The absolute value of 3 is 3, so I'm not going to write absolute values, I'm just going to write a 3. The n's do not reduce. As n goes to infinity, the n's go to 1. The plus 1 doesn't matter, n over n is 1. As n goes to infinity, this thing goes to 1, so you don't include it over here. Any n terms, any log terms, they reduce, they go to 1 as, they don't reduce, they go to 1 as n goes to infinity. So this is the answer to that limit. We make it less than 1 because we want it to converge, and that's what makes a ratio test converge. So the absolute value of x is less than 3. And I just looked at my, you didn't see me, but I just looked at my directions again. We want to determine the interval of convergence. If we were asked to determine the radius of convergence, it would be sitting right there. That is the radius of convergence. So, x is between -3 and 3. Here is the interior of our interval of convergence. We're centered at 0. Yeah? Centered at 0. It's a Maclaurin. We're centered at 0. Yeah? Centered at 0, -3 to 3 is our interior of our interval of convergence. Now we need to check the boundaries. So I'm going to check x is equal to -3, and then I'm going to check x is equal to 3. I go back to my original series, the one with the -1 in it. You have to pull down that -1. -1 to the n plus 1. in place of x, I'm putting a negative 3. Negative 3 to the n plus 1 divided by 3 to the n times n. We want to determine if this thing converges or diverges. Okay, this negative 3 to the n plus 1, I'm going to rewrite that as something. So first I'm going to rewrite this. Now I'm going to rewrite this. I'm going to write it as negative 1 to the n plus 1 times 3 to the n plus 1. Okay. Now, this right here, that is negative 1 to the 2n plus 2. Focusing on the 2 right there. That 2 is going to make this exponent always, the 2n is going to make it even. If I add 2 to any even number, it's still even. Negative 1 to an even power is always 1. Okay? So this is 1 times, okay, the 3 is reduced, leaving a 3 on top, over n. This is 3 over n. Okay? Alright, because of the 3. This is not a harmonic because of the 3. But I can easily take the 3 out and make it the harmonic series. So this is the diverging harmonic series. Okay. Little work to get there. Let's go put in the other endpoint 3 now. If I put in 3, and again, I'm going back to my original formula. I'm going to put 3 in for x. So I have negative 1 to the n plus 1, 3 to the n plus 1, over 3 to the n times n. Okay, does this converge or diverge? Well, this one is still alternating because that's the only negative 1 involved. The 3 is reduced to 3 over n. This is alternating in sign, decreasing in magnitude to 0, therefore converges by AST. You guys, in the ratio test, this takes it takes care of all of that. All you have to do is say converges by AST there. So the interval of convergence is negative 3 to 3, not including the negative 3 because that one diverged, but yes, including the 3 because that one converged. Part C. Let P sub 4 be the 4th degree Taylor polynomial for f about x equals 0. Okay, so we have the 4th degree Taylor polynomial. Using the alternating series error bound, use the alternating series error bound to find an upper bound for the error, so just the error. Okay, if I use the 4th degree term for the approximation, then the error bound will be the 5th degree term. Let's go to our f of x. Here's f of x, yeah? I'm about to lose power. Let me plug in real quick, sorry. Okay, my computer. Okay, alrighty. So we used the 4th degree Taylor polynomial for our sum. The 5th degree term is our error. So I'm going to write that 5th degree term, but I'm putting 2 in for x. Remember, you guys, error, no x's in error. No x's ever in error, all right? I'm replacing that x with a 2, writing everything else down. This is the error bound. That's just it. This is our answer. I don't need to do anything else. That is my answer. Okay, real quickly the way they scored this. 1 point for uses the 5th degree term, 1 point for the answer. So if you choose to simplify, it has to be correct to get your answer point. Okay, the ratio test part. This was worth 5 points this year. 1 point for sets up the ratio. 1 point for computes the correct limit of the ratio. 1 point for the interior of the interval of convergence. 1 point for considers both endpoints. And then 1 point for your analysis, and the answer, the interval of convergence. I squeezed that in there. Alrighty. Okay, oh, and then for this part. For part A, they gave 1 point for the first 4 terms. First 4 terms, 1 point for the general term. Okay. Okay, next up we're going to go do number 7. Okay, number 7. This was the one from 2021. Okay, look at how low the global average was. That's really low for us as well. So, really, really low. Let's see what made it so hard, okay? The function g, now this is, number 6 is the last FRQ. Last FRQ on the whole exam. So by the time students get to this, they've been working now for about at least 3 hours, probably a little bit more than 3 hours, and their brains are a little bit tired, okay? So you give yourself a mental slap and you get yourself into gear. All right, the function g has derivatives of all orders for all real numbers. The Maclaurin series for g is given by this series on its interval of convergence. State the conditions necessary to use the integral test to determine convergence of this series. Use the integral test to show that this converges. Okay, so the first part did not include g at all. All we're asked to do is do the integral test on this. So we will. Okay, state the conditions. The function f of x is equal to 1 over e to the x is positive, continuous, and decreasing for all x greater than or equal to 0. It's very true. It's e to the x. It's always positive. So, all right. So that takes care of our conditions. Since I said that and they asked me to do that specifically, I know I got a point for that, and I did. All right. So now we're going to use the integral test. 0 to infinity. 1 over e to the x dx. All right, how to integrate that? So in class I'll ask you how to integrate that, and some bright person will tell me move the e to the top and give it a negative power, and now the antiderivative of that is negative e to the negative x, because if we take the derivative of this, we get that. From 0 to b. Alrighty. Now, I have a negative power. Don't try to put infinity in for a negative. Just go ahead and move it. I'm going to rewrite this back as 1 over e to the x. So this is limit as b goes to infinity of negative 1 over e to the x from 0 to b. Okay, b goes in for x, b goes to infinity, 1 over infinity is 0. So this is 0. minus. Now I'm putting 0 in for x. It's a negative, so minus a negative 1 over e to the 0 is 1. So this is just 1. The value of this integral is 1. All right? So I can say that the integral 0 to infinity of 1 over e to the x dx converges. So the series n equals 0 to infinity 1 over e to the n also converges by integral test. This was worth 3 points. 1 point for the conditions, 1 point for the limit expression, either for the integral or the antiderivative. So that limit expression there was worth a point that year. 1 point for the evaluation of the integral and the conclusion. So the evaluation included the antiderivative and your plugging in of your boundaries. So 3 points. So ask yourself, could you have gotten those 3 points? If so, you're already ahead of the global average and the KHS average. Okay, part B. Use the limit comparison test with this series to show that this series converges absolutely. Converges absolutely. All right, well, for absolute convergence, I need to show that even without alternating, this thing converges, even without alternating. So I'm asking myself, without the negative 1, if I replace the negative 1 with a 1, I need to be able to say that that converges. And they tell me how to do it. They tell me to use the limit comparison with this thing. Okay? So 1 over e to the n converges by what test? What test? That's a ratio test. R would be 1 over e. 1 over e is less than 1 over e is less than 1, therefore converges. Okay? Alright, so I know this one converges. Now I'm going to use limit comparison test. So limit as n goes to infinity, 1 over 2 to the 2e to the n plus 3 divided by 1 over e to the n, which is the same as multiplying by e to the n over 1. Okay, as n goes to infinity, the plus 3 will not matter, and I'm left with e to the n over 2e to the n. That limit is 1/2, which is finite and positive. Finite and positive. You do not have to say that it is finite and positive. You don't have to say that. I apologize for my fingernails. That's so embarrassing. I was out gardening today, and so I have really yucky fingernails. Okay, anyway, you do not have to say that it is finite and positive. Just saying that it is 1/2 is plenty. I can say, therefore, since this one converges, this one will converge as well. Okay, now, in this question, they did not say that I had to state the conditions. Since they did not say I had to state the conditions, I don't have to state the conditions. If you're nervous and you want to state them anyway, go for it. Okay, you can say that both series terms are greater than or equal to 0 for n greater than or equal to 0. Okay, this was worth 2 points. 1 point for what they called sets up limit comparison test. And then 1 point for your explanation. That would be explanation. Alright, so that would be the answer to your limit and then your conclusion. Alright, part C, determine the radius of convergence of the Maclaurin series. The radius. So we're not going to have to check the boundaries. Okay, that's the worst part of the interval of convergence test, just the radius. So I'm going to set up, I keep wanting to put an X there, set up the ratio test. So now I'm going to G, and G was up here. There's G. You got it? Oh yeah, there's G. So I'm not going to put the -1 because I have absolute values. The ratio test has absolute values, so no -1. Go to your X. Replace every n with n plus 1. Replace every n with n plus 1. So I have x to the n plus 1 divided by 2e to the n plus 1 plus 3 times, and now you write the reciprocal of your nth term. So the 2e to the n plus 3 goes on top. The x to the n goes on the bottom. There's our setup for the ratio test, always worth a point. Always worth a point, the setup for the ratio test. Okay, now, what is this going to give? So, the x's reduce, leaving a single x on top. Put your absolute value bars around it. So a single x on top. On the bottom, the plus 3's will not matter. The 2's reduce, and it leaves an e on the bottom. Let me do that again. The plus 3's won't matter. As n goes to infinity, the plus 3's will not matter. The 2's reduce, leaving an e on the bottom. Okay? Make that less than 1. Absolute value of x is less than e. Therefore, the radius of convergence is e. 3 points. 1 point for sets up the ratio test, the setup. 1 point for computes the limit correctly. 1 point for your answer. Okay. Part D. Use the first two terms of the series this series are used to approximate g of 1. Use the alternating series error bound to determine an upper bound for the error of the approximation. Well, the first two terms are used. Therefore, the upper bound is the third term, right? The third term. Well, n starts at 0, so n equals 0 will be the first term. N equals 1 will be the second term. Therefore, the third term will be when n is equal to 2. So I'm going to put 2 in for n, ignoring the -1 because upper bounds, the error bound is always positive, and it will be 1 over 2e squared plus 3. And that's just it. That's our answer. 1 point for the answer. Okay, so what do you guys think? Was this as hard as everybody made it out to be? I don't think so. I don't think it was hard. Look back over this problem. What was the hardest part? I think that this one threw them. I think this one threw them. For absolute convergence, you ignore the -1. See if that converges. Okay. All right. That's it. So, guys, I would love for you to spend the last, 15, 20 minutes of class doing at least one more FRQ here. So do a total of at least 3 FRQs for homework. At least. Preferably all of these. At some point before the AP exam, do all of these. But I will be checking to see if you did 3 more of these. Okay? Alrighty. That's it. Get to work.